Hi ladies, this is lesson 6.2, and in this lesson we're looking at applying properties of rational exponents. So we've done these properties before, but we were doing it just with integer exponents, and now we're looking at the whole rational set of numbers. So a couple things that are similar to what we've done in previous lessons at the beginning of chapter 5, but looking at this term, simplest form of a radical. So if a radicand has no perfect nth powers as factors, and the denominator has been rationalized, which means there's no radical sign in the denominator, then the radical is in simplest form. And then our second term is like radicands, and this is just like terms, and again we've used like terms having the same exponent before, but now we're looking at radicals. So like radicals mean that there's the same index and the same radicand. Okay, so on this next slide, let's look at some properties of rational exponents. So the first property, a to the m times a to the n, we're adding these two. We're adding those two exponents. So that's 4 to the 1/2 times 4 to the 3/2. So that's 4 to the 1/2 plus 3/2, which is 4 to the 4/2, which is 4 squared, which is equal to 16. In the second property, this is a powers of powers property. So a to the m to the n is a to the m times n. So 2 to the 5/2 times 2 is 2 to the 10/2, which is 2 to the 5th power, which is 32. In the third example, ab to the m is the same as a to the m times b to the m. We're distributing that exponent, and we're only doing that because we're multiplying a times b. So 16 times 4 to the 1/2 is 16 to the 1/2. Times 4 to the 1/2. So 16 to the 1/2, that's the square root of 16 times the square root of 4. So the square root of 16 is plus or minus 4, and the square root of 4 is plus or minus 2. So our solution is positive or negative 8. In the fourth example, we have a negative exponent, and when we have a negative exponent, we need to move it to the denominator. So we have a negative exponent in the numerator. We're going to move that exponent to the denominator, and then it changes signs. In number 4, we have this restriction a does not equal 0 because we cannot have any number over 0 that's undefined. So here we have 25 to the negative 1/2. That's the same as 1 over 25 to the 1/2, which is 1 over the square root of 25, which is 1 over plus or minus 5. In this fifth example, again, since we have n in the denominator, when we move it to the numerator, it changes signs. So dividing is the same as multiplying by its reciprocal. That's what division is. So a to the m over a to the n is the same as a to the m minus n power. Again, we have this restriction a does not equal 0 because we cannot have 0 in our denominator. That creates an undefined quotient. So here we have 3 to the 5/2 over 3 to the 1/2. So that's 3 to the 5/2 minus 1/2. And we get 3 to the 4/2, which is 3 squared, which is equal to 9. And then in this last example, we have a over b to the m. That's the same as a to the m over b to the m. Again, b does not equal 0 because if b was 0, then our solution would be undefined. So here, 27 over 8 to the 1/3 is the same as 27 to the 1/3 over 8 to the 1/3. So that's the cubed root of 27 over the cubed root of 8, which is 3 over 2. Now in this next example, we're going to use some of these properties of exponents, and we're going to use that to simplify our expression. So here we have 9 to the 1/2 power times 9 to the 3/4 power. 9 to the 1/2 power, that's the square root of 9. And 9 to the 3/4 power is the 4th root of 9 cubed. So when we look at our properties of exponents, we're going to add these 1/2 and 3/4 because our base is both 9. So 9 to the 1/2 plus 3/4 power is 9 to the 2/4 plus 1/4, which is 9, plus 3/4 rather. 3/4. So that's 9 to the 5/4 power. That's the same as 3 squared to the 5/4 power. And now again, if we apply our properties of exponents, that's 3 to the 10/4 power because we're multiplying our exponents. Which is the same as 3 to the 5/2 power. And 3 to the 5/2 power is the square root of 3 to the 5th power. Now, remember rationalizing exponents, when we have it in simplest form, we cannot have perfect squares if we're taking the square root. So we're going to pull out 4 of those 5 3's, and we get 3 squared times the square root of 3, which is 9 times the square root of 3. So that one, we used a lot of those properties. We added exponents, we multiplied exponents, and we factored out perfect nth powers. So let's look at this second one. In this next example, we have 7 to the 2/3 times 5 to the 1/6, and that's all to the 3rd power. Now, since these have different bases, we cannot combine those two exponents, but we can take 7 to the 2/3 power times 3, and we're going to multiply that by 5 to the 1/6 power times 3. So we get 7 squared times 5 to the 3/6, which is 5 to the 1/2. 7 squared is 49, and 5 to the 1/2 is the square root of 5. And then in this third example, we do have the same base, so we're going to take the difference of those exponents. So 3 to the 5/6 minus 1/3 is 3 to the 5/6 minus 2/6. Five minus 2 is 3, so we end up with 3 to the 3/6, which is 3 to the 1/2, which is the square root of 3. And then in this last example, again, we do not have the same base, But let's think about what this is asking. They're both to the same power. So 16 to the 2/3 power divided by 4 to the 2/3 power, all to the 4th power, is the same as 16 over 4 to the 2/3 times 4 power. 16 over 4 is 4 to the 2/3 times 4th power, which is 4 to the 8/3 power. So the next piece on your note sheet is identifying properties of radical or product property of radicals and the quotient property of radicals. So if we have a times b, the nth root of a times b, that's the same as taking the nth root of a and multiplying that by the nth root of b. And our quotient property is similar. The nth root of a divided by b is the same as the nth root. Oh, here we go. The nth root of a divided by the nth root of b. And again, here b cannot equal 0 because if b was equal to 0, then our expression would be undefined. So we've identified a radical in simplest form, but again, it's in simplest form if it has no perfect nth root powers as factors, and the denominator has been rationalized. So again, that means that there's no radical sign in the denominator. So let's look at how to get rid of some of those. So here we have the 5th root of 27 times the 5th root of 9. Well, the 5th root of 27 is the 5th root of 3 cubed, and the 5th root of 9 is the 5th root of 3 squared. So the 5th root of 27 times 9 is the 5th root of 3 to the 5th. Because again, when we multiply and we have the same base, we add those exponents. So the 5th root of 3 to the 5th is equal to 3. In this next example, we've got the cubed root of 192 over the cubed root of 3. So that's the same as 192 to the 1/3 and 3 to the 1/3, which is 192 divided by 3 all to the 1/3 power, or the cubed root of 192 divided by 3, which is the cubed root of 64. The cubed root of 64 is 4. So these next couple, I want you to pause the video while you work, and when you unpause, I'll show the solution. Try these couple on your own, applying properties of exponents. So in the first example, you should get a solution of 1 over 30. And in the second example, you should get positive or negative 7 as your solution. Now this next example asks you to write the radicals in simplest form. And for this one, we're going to use the product property of radicals that says the nth root of a times b is the same as the nth root of a times the nth root of b. So if we look at our factors of 128, in order to write this in simplest form, there can be no perfect 5th powers. So we can factor 128 as 32 times 4. 32 is equal to 2 to the 5th power. So the fifth root of 128 is the fifth root of 32 times 4, which is the fifth root of 2 to the fifth times 4. So when we simplify this, the fifth root of 2 to the fifth times the fifth root of 4 is equal to 2 times the fifth root of 4. So again, to have this in simplest form, the fifth root of a number to the fifth power is that number. So the fifth root of 2 to the fifth power is 2. And we're multiplying that by the fifth root of 4. Now this next statement gives you your second definition. So radical expressions with the same index and radicand are called like radicals. So we can use the distributive property to add or subtract like radicals. So here we've got 2 times 12 to the 2/3 power plus 7 times 12 to the 2/3 power. These are like terms, so we can add 2 and 7 together. So we get 9 times 12 to the 2/3 power. Now we need to simplify this. So 9 times 12 to the 2/3 power is equal to 9 times the cubed root of 12 squared, which is 9 times the cubed root of 144. If we factor 144 looking for perfect cubes, we can factor 144 as 8 and 18. So this is 9 times the cubed root of 8 times the cubed root of 18. The cubed root of 8 is 2, so 9 times 2 times the cubed root of 18 is equal to 18 times the cubed root of 18. And then we're going to do the same thing here. We're looking for any perfect fourth roots that we might find. So 48, that's the same as the fourth root of 16 times 3. Minus the fourth root of 3. So the fourth root of 16 times 3 is the fourth root of 16 times the fourth root of 3 minus the fourth root of 3. The fourth root of 16 is positive or negative 2. It's positive or negative 2 because 4 is an even number and 16 is greater than 0. So positive or negative 2 times the fourth root of 3 minus the fourth root of 3. Now these are like terms. So positive 2 minus the fourth root of 3 is equal to the fourth root of 3. And negative 2 minus fourth root of 3 is negative 3 times the fourth root of 3. So these are both our solutions. Either 1 times the fourth root of 3 or negative 3 times the fourth root of 3. These next two examples, please pause the video while you work and try these on your own, and then you can unpause for the solution. So in this next example, number 3, we need to rationalize the denominator. So right now we have the cubed root of 9. Now 9 is a perfect square, but it's not a perfect cube. So we need to make the denominator a perfect cube and take the cubed root of that. So we're going to multiply by 1, the numerator and the denominator, by the cubed root of 3. And when we do that, in our denominator, we end up with the cubed root of 27. And our numerator is the cubed root of 5 times the cubed root of 3, which is equal to the cubed root of 15. in our denominator, the cubed root of 27 is equal to 3. So our final answer is the cubed root of 15 divided by 3. In our second example, the fourth root of 6 is in both of these terms, so we can add these together. So 6 plus 2 times the fourth root of 6 is 8 times the fourth root of 6. Then our next section is about applying properties of rational exponents using variable expressions. So when n is odd, x to the nth power is just x, but when n is even, x to the nth power, the nth root of x to the nth power equals the absolute value of x, so positive or negative x. So let's look at a couple examples involving variables. So the fifth root of 32 is the same as the fifth root of 2 to the fifth times the fifth root of x to the 15th. The fifth root of 2 to the fifth is equal to 2, and the fifth root of x to the 15th is x to the 15 over 5 power. So we have 2 times x cubed. So we're assuming right now that all variables are positive. In the second example, we need to distribute this 1/2 power. So we have 36 to the 1/2 times m to the 4 halves times n to the 10 halves. And that's equal to positive or negative 6 times m squared times n to the 5th. And then the last one, or the next one, letter C, that's a to the 9th to the 1/3 power over b to the 6th to the 1/3 power. So that's a to the 9 over 3, which is a cubed, to over b to the 6 over 3, which is b squared. And the last one, 42x to the 4th, z to the 7th over 6x to the 3 halves, y to the negative 3rd, z to the 5th, is the same as 42 over 6 times x to the 4th over x to the 3 halves times 1 over y to the negative 3rd times z to the 7th over z to the 5th. So 42 divided by 6 is 7. X to the 4th divided by x to the 3 halves, we're going to subtract those variables. So that's x to the 8 halves minus 3 halves, which gives us x to the 5 halves. Now, for 1 over y to the negative 3, we need to move that negative exponent to the numerator. So we end up with just y cubed. And then in the z term, we're just taking the difference of those exponents. So it's z to the 7 minus 5, which is z squared. So if we were to rewrite this, we would say 7 y cubed z squared x squared times the square root of x as our final answer. And I don't believe actually this one is on your note sheet. And this next one is example 6 on your note sheet. So we're adding and subtracting expressions involving variables. So again, if we have like radicals, we can subtract those terms. So this is 10 minus 6 times the 5th root of y. which is 4 times the 5th root of y. And then in the second one, 3a squared b to the 1/4 plus 4a squared b to the 1/4. Again, these are like radicals, so we can add those together, and we get 4 plus 3 is 7, a squared b to the 1/4. And then in this last example, I want you to pause the video while you work, and then you can unpause for the solution. And this is the last example, last two examples. So in this first example, our answer is 2x squared y z cubed times the cubed root of x z squared. And the reason we have x squared and then later the cubed root of x is because 7/3, so we have 7 x's and we're looking for perfect cubes of those. So if we pull out 6 of those, that's x squared, and then we have 1/3 remaining. So that's why later we have this cubed root of x. And then the same with y. 3/3 is y to the first power, which is just y. And then z to the 11/3 is z to the 3/3 times z to the 3/3 again times z to the 2/3, which gives us z cubed times the cubed root of z squared. And this next example actually should be 7 times the cubed root of a to the 5th minus 7 times the cubed root of 128 times a to the 5th. So if you need to rework that, this is the expression you should be using. So 7 times the cubed root of 2a to the 5th is 7 times a times the cubed root of a squared. And then here we can factor out that 128 as 8 and 16. So here we get 7a times the cubed root of a squared minus 14a times the cubed root of 16, which is 8 and 2, a squared. So 7 times the cubed root of a squared minus 28 times a times the cubed root of 2a squared. Oh, and I apologize, I dropped a 2 here. So if you didn't have that 2, then you would not be able, these are not like radicands, but actually this should be 7a times the cubed root of 2a squared minus 28a times the cubed root of 2a squared. So now we do have like radicands and we have like terms. So 7 minus 28 equals negative 21a times the cubed root of 2a squared. So again, this actually is what the problem on your note sheet should say. 7 times the cubed root of 2a to the 5th minus 7 times the cubed root of 128a to the 5th. So if you're working through your note sheet, your solution that you get should be negative 21a times the cubed root of 2a squared. So if you have any questions, please let me know and we can go over this next time I see you in class. Thank you.